Hello everyone, in this video we'll be solving a hard problem number 4, median of two sorted arrays. The problem statement is we are given two sorted arrays nums1 and nums2 of size m and n respectively. We need to return the median of the two sorted arrays. As a follow-up, the solution's time complexity should be O of log of m plus n. In example number 1, nums1 contains 1 and 3 and nums2 has 2 in it. If we combine the array together, it will have 1, 2 and 3. As median is the centermost element in an array, the output should be 2. In cases when there are an even number of elements in an array, the median is the average of the two numbers at the center. If we try to solve this problem without considering the time complexity requirement, it is a very easy problem to solve. All we need to do is, using two pointers, run and iterate through both of the arrays simultaneously and build a combined array. And after the combined array is created, based on the length of the combined array, we can calculate the median. Either take the centermost element or calculate the average of the two elements in the center. But with this solution, our time complexity will be O of m plus n, as we are running the iteration on both nums1 and nums2 to build the combined array. And the space complexity is also going to be same, as we are creating a combined array of all of the elements in nums1 and nums2. Now let's discuss a different approach where we can cater to the time complexity requirement. Whenever I see a time complexity of log n, the first thought that comes to my mind is to use binary search algorithm. But it's not very evident how we can use binary search algorithm to this kind of a problem. Before we talk about that, let's discuss few of the basics which we can use to solve this problem and how binary search will be useful. Between the two arrays, we have a total of 11 numbers and the midpoint is going to be 5 if we do a round down. Based on that midpoint, the median of the two arrays should be 3, as it is the centermost element in the combined array and it has 5 elements on the left and 5 elements on its right. Now we need to determine how many elements on the left hand side of the median should be coming from n1 and n2. As we know the length of the combined array, we know how many elements should be there on the left hand side of the midpoint. So let's start with an assumption that we need half of the elements in the smaller array between n1 and n2, which will come in on the left hand side of the combined array. Because n2 is smaller, we'll use that to apply binary search algorithm. So we'll use two pointers, left and right, left pointing at the first element, that is index 0, and the right will be pointing at the last element, that is index 3. Using left and right pointer, we can calculate the midpoint in n2, which will be pointing at number 2. We continue with the assumption that the first half of n2 will be there in the left hand side of the combined array. So we have identified 2 elements out of the 5 elements that we need on the left hand side. So based on those two numbers, we can easily figure out how many numbers we need from n1 to be placed in the combined array. That is 5 minus 2, so we need 3 numbers from n1. And as the array is already sorted, we'll be taking the first 3 numbers from n1. So we'll draw a partition between 3 and 4. Now that we have 5 numbers on the left hand side, we now have to calculate the median. Because there are odd numbers between the two arrays, we don't need to calculate the average of two numbers like we did for even numbers. If we look at the combined array, after we have the first 5 numbers identified, the next number is the median, because after that we have 5 another numbers on the right hand side. Similarly, now that we have 5 numbers between n1 and n2, the median should be the number right after the partition that we drew in n1 and n2. We can't say for sure if it will be in n1 and n2 unless we compare the next value. So the median will be calculated by applying the math.min operation on the next element after the partition, which is 4 and 3. So between those two numbers, 3 is smaller, so that will be our median. This is only possible if we have a total of odd elements between the two arrays. If we have an even number, we need to calculate the average. So that is a different approach which we'll be discussing next. We have so far covered a very happy and basic case where we did not have to play around with the left and the right pointer using binary search algorithm. In the next example, we'll try to cover that and also try to solve a case where there are a total of even numbers between the two arrays. Let's work with this example where the total number of elements are 12 and the middle is going to be 6. The median of this combined array is the average of 4 and 5, which is 4.5. Similar to the previous approach, we'll use binary search algorithm to solve this problem. We'll apply it on the smaller array, which is n2. Starting with the left pointer pointing at index 0 and the right pointer pointing at index 3, the midpoint is going to be index 1, which is number 2. So we'll draw a partition right between 2 and 3. So we have so far 2 elements on the left hand side. As the middle is 6 and we already have 2, we need 4 elements from n1. So we'll draw a partition right between the two 5s. Now before moving any forward, we need to first verify that the elements that we have on the left hand side are all valid. That is, we need to make sure that the values on the left hand side are smaller than the values on the right hand side. So if you look at the last value in n1, which is 5, it is greater than the next element on n2 after the LHS. So this makes it invalid. We cannot have 5 on the left hand side and 3 on the right hand side. The array is no longer sorted. So we need to fix that. The formula that we are using here is the max of LHS should always be less than or equal to min of RHS. This applies to both the arrays. The max of LHS on N1 should be less than or equal to the min of RHS on N2 and vice versa. We don't need to compare within the same array because the array is sorted. So the 5 in this case is always going to be less than or equal to the next element in N1. So we need to limit this comparison to the other array. Now that we know that the condition is not suffice, we need to update our pointer. So the left pointer should be changed to midpoint plus 1. This change will also help us define or take more elements into RHS from N2 than we were taking before. Now with left pointer pointing at 2 and right pointer pointing at 3, the midpoint is going to be 3, which means we'll be taking 3 elements from N2 and the remaining 3 will be coming from N1. With this change, the partition will now be between 5 and 5 at index 2 and index 3. Now we'll repeat the same check to look at the max of LHS and compare it with the min of RHS. Is the condition sufficed? The min of RHS is 4 and the max of LHS is 5. As the condition is not sufficed, we'll repeat the same cycle of updating the left pointer. So the new value will be left pointer is equals to mid plus 1, which is equals to the right pointer. So both left and right pointer are pointing at the same value. The midpoint is also going to be the same. This means that out of the 6 values that we need on the left hand side, we are getting 4 values from N2. So we only need 2 values from N1. So we'll move the partition again towards the left hand side. Now it's between 4 and 5. Repeating the same check again. So max of LHS is 4 this time and the min of RHS is 5. So the LHS is coming from N2 and RHS is coming from N1. And because the condition is sufficed, we can calculate the median. Because we have a total of even numbers between the two arrays, we need to calculate the average of the centermost numbers. And to get those two numbers, we'll use this formula, which is max of LHS between N1 and N2 plus min of RHS between N1 and N2 divided by 2. The max of LHS is between 4 from N1 and 4 from N2 that's based on the partition that we have drawn. Between these two numbers, the max is 4. And for RHS, as there is no RHS on N2, the value will be between 5 and infinite. So 5 is the minimum. So on the right hand side, we'll get 5. So the average is between 4 and 5, giving us the total 4.5. I hope you were able to understand how we are using binary search algorithm to solve this problem. Because the numbers in N1 in this example were greater than the numbers in N2, we were updating the left pointer. But if it was not the case, then we would have updated the right pointer to shift towards the left to accordingly get the right numbers on the left hand side. This approach is only possible because the input arrays were sorted. If it wasn't, then the first option that we discussed would have been a more suitable choice. There are a couple of edge cases that we haven't discussed. For example, What if all of the elements that we need on the left hand side are only in one of the two arrays? For example, it's only in n1 or n2. In those cases, we need to make sure that we are updating the partition accordingly. And when calculating the math.min or math.max between the two numbers, use infinity or positive or negative when there are no numbers available in the other array. With this solution, our time complexity is O of log of min m comma n. The log is because we are using the binary search algorithm, and min of m comma n is because we are running the binary search algorithm only on the array which is of smaller size. And the space complexity is O of 1, that is constant space, as we are not creating any collection to store the combined array. We are only using couple of pointers to determine the range of the partition. Let's walk through the solution in Python. Here's the solution in Python. As we want to run a binary sort algorithm on the smaller array, we'll make an assumption that nums1 is always going to be smaller than or equal to nums2. We'll verify that by comparing the length of the two arrays and then reversing the order if the condition is not met. After that, we initialize a couple of variables to record the length of the two arrays and the low and the high pointer, which will be used to run binary search algorithm. Now we can start the binary search algorithm using the while loop, where low pointer should be less than or equal to high pointer. Inside the while loop, I am calculating the partition for both of the arrays, that is nums1 and nums2. After calculating the partition, we need to make sure that the values on the left hand side of the partition are less than the values on the right hand side. To do that, we need to know the minimum of the right hand side and the minimum of the left hand side for both of the arrays. I am doing that in the next 4 lines of code, while also handling if the partition is on the far left or the far right side of the nums array. Now we do the comparison of the two arrays based on the partition, where the maximum of the left hand side of nums1 should be less than or equal to the minimum of the right hand side of nums2 and vice versa. If the conditions are suffice, based on the total number of elements across the two arrays being even or odd, I am using appropriate formulas to calculate the median and return it. If the condition is not suffice, it means the partition that we have placed in nums1 and nums2 are not correct. We need to revise it. If max left of nums1 is greater than the minimum right of nums2, it means the median is on the left hand side, so we need to shift the high pointer or else shift the low pointer. To avoid compile time errors and edge cases where the input array is not sorted, we'll throw a value error exception if the while loop exits without returning any output. This code, when submitted on LeetCode, beats nearly 53% of the submissions in terms of runtime and 59% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.